So, good afternoon, everyone. Welcome to the fifth session of problem solving for the course of structure analysis. Let me share my screen first. Yeah, I think the screen is visible to you all. If someone has any problem in between, they can ping me or just open your mic and tell me, is there any confusion regarding the concept we are just discussing in this problem solving session? And we'll try to cover as much question and concept based upon the topics which are covered in the week 5 related to conjugate B method. So, my name is Pranam Mahajan. I am a PMRF scholar in the Department of Civil Engineering in Structural Engineering Division, IIT Madras. I am allotted as a teaching assistant for the course of structure analysis under NPTEL. And in previous week, what we have seen in previous week, in week 1, we started with seeing equilibrium equations. Second, calculation of reactions. Then we will move to uh, determine the shear force diagram and the bending moment diagram for different beams. Then on week 2, we have moved to trusses. So we have told that truss is a two force member. What do you mean by two force member? That it can carry compression and tension forces along its axis. And we have seen how to determine the forces in the trusses using method of joints and method of sections. Out of which, in method of joint, we have seen that if we take the summation of forces in horizontal and vertical direction equal to 0 at any then we will be able to calculate the unknown forces at a particular joint based upon the number of unknowns that are available. In method of section, we use a cut plane and we cut the section into in such a way that it will be divided into two parts, such that the smaller portion in generally that we consider will provide us the unknown force that we are required to calculate in the complex truss member. Then in V3, we have moved to calculation of deflection in trusses. Calculation of deflection in trusses. How we have done that? Using unit load method and principle of virtual work. So what we have told here is that uh, if you require to calculate the horizontal and vertical deflection at any joint of the truss, what you have to do, you have to apply a unit load at that particular direction. Suppose you have to calculate the vertical displacement, so apply a unit load at that particular joint in vertical direction and calculate the member forces due to that particular joint removing all the external loads that are applied over it, and again calculate the forces using the external joints that are applied over it, and then use the principle of superposition and principle of virtual work, such a way that internal work done will be equal to external work done, and that will give you the deflection at a point that you have seen, like that delta is equal to n and l upon ae, where n is the force due to, and this is the force due to external loads. Small n is the force due to unit load, and rest are all the geometrical parameters of that particular member. And then if you put in that equation, you will get to know the value of deflection at that particular point. In fourth week, what we have done in week four, we have determined the deflections. Uh, Let me go through you to that slides. So what we have done is we have used the equation of elastic curve to determine the slope and deflection at any point using moment of area method. Okay, so this is what we have done in the previous week. So we have used moment area method to determine slope and deflection at any point. Okay, this is what we have covered till now. In week 5, how we have started? In week 5, we have seen that how the conjugate beam method can be applied on beams and on frames. So week 5, what we have covered? We have covered conjugate beam method. So what we have done, suppose we have an uh, simply supported beam. This is our simply supported beam, which is subjected to non-uniform loading at various points. And if we draw the bending moment diagram, it will somewhat look like this. Okay, it will somewhat look like this. Yeah, so this is your bending moment diagram. And if you draw the shear force diagram also will be like what you have seen previously also, that how you can define the shear force diagram for different sections. Okay, so this will be the shear force diagram of the beam. So all these things are in static condition, wherein the variables are static variables are load, shear, and moment. Now to determine the deflection and slope at any particular point, we convert them into kinematics. Okay, so what we will do, we will take a beam. See how its deflection profile looks like. So this is the deflection profile of the beam. So in this, the kinematic variables will be your deflection represented by yx, your slope theta x, and your curvature. Okay, so these three parameters are there in kinematics. So is there any relation between them, that how the statics and kinematics can be interrelated to each other? So in previous week we have seen that uh, m is equal to ei d2y by dx square minus, or I can write in different way, that d2y by dx square is equal to minus m upon ei, then d cube y upon dx square is equal to minus v upon ei, and d4y upon dx4 is equal to q upon ei. Whereas here all the variables are related in kinematics in such a way that q will provide you 1 by rho, that is curvature. V will provide you theta, that is slope, and m will provide you deflection, that is y. Okay, so that is how we have interrelated both of them. So we can say that that statics, or this system 1, is a conjugate of system 2, which is this uh, kinematics kind of a thing. Okay, so now let's take a problem, then it will be easy for you to understand that what are the concepts we are covering here. So suppose you have a simply supported beam carrying UDL over its whole length. So if you draw the bending moment diagram for this beam, it will be like this, and it has a maximum value of QL square upon 8, and the equation of this curve will be QL by 2 into h minus QH square upon 2, that will give you bending moment. So this is your bending moment diagram. So now what you have to do, you have to take this bending moment diagram as the loading diagram of the conjugate beam. Okay, so now this will be your loading diagram. Okay, fine. And it has a maximum value of QL square upon 8 EI, because it is M by EI diagram. Okay, why we have done is because you can see here the moment, bending moment upon EI will give you the deflection at any particular point. Okay, so you divide the whole diagram in such a way that your uh, bending moment will correspond to the deflection of the conjugate beam. So this will be your loading diagram for the conjugate beam. Okay, Now your this total load Q will be equal to integration of 0 to L f of x into dx. So how you will determine this load? It will be Q, since it is parabolic, so it will be 2 by 3. Maximum value comes out to be QL square upon 8 EI into length. So this value will be QL cube upon 12 EI. Okay. So this is the maximum value. Now for the reaction purpose, suppose this is your AY, AX, BY. Your AY is equal to BY will be equal to QL cube upon 24 EI. Okay. Now if you want to find the bending moment of this, it will be like this. This is your AY. AX will be equal to 0 at any particular point C. Suppose this is your uh, shear at that particular point, and this is your bending moment at that particular point. And at that central point, you have a maximum value of QL square upon 8 EI. Okay. So what will be the value of this MC? So MC will be equal to moment of this area is area diagram. So that will be equal to 5 by 384 into QL cube upon EI. Okay. Now this shear will correspond to slope at that particular point. So your theta A will be equal to minus of theta B will be equal to QL cube upon 24 EI. And your moment will correspond to deflection. So your delta C will be equal to 5 QL cube upon 384 EI. So this is how you will solve for this problem. If you require to calculate deflection at any particular point, you will take the moment at that particular point and determine their values. And if you determine to find, you want to find the slope at that particular at any point, you will take the shear at that particular point for the M by EI diagram, and it will provide you the value of slope at that particular point. So this is conjugate beam method. Okay. Uh, However, this has effect of supports also, because you have to change the supports to satisfy the kind of loading that is there at a particular joint. So for the real beam support, when you convert it into conjugate beam, some values of some supports will get also changed. So if I write the effect of supports, it is like your hinge joint. So your hinge joint, for I think I will move it a little bit down, and top I will write as this is real beam support. This is your conjugate beam support. So your conjugate beam will also have hinge at that particular point. No change will occur. For roller support, it will also remain the same as a roller support. Okay. If you have fixed end at any particular point, it will be changed to the free end at a particular point. Okay. If you have any external hinge in between the beam, it will be changed into internal hinge at that particular point. And if you have any internal hinge at any particular point, it will be changed into external hinge at that particular point. So all these effects you need to be considered when you will be constructing your conjugate beam method from the real beam method. Okay. So this all things you need to remember or try to gain the concept what is being taught and then apply this for the conjugate beam. So take another example, a simple example. You have a cantilever beam subjected to point load at the tip. Okay. So mark it as if this is your x direction, this is your y direction. So this is your real beam. So draw the bending moment diagram for this. Okay. So the maximum value will come out to be P into L. If this is your L, it will come out to P into L, and the x at any point will be equal to P into L minus h. So this is your bending moment diagram. If you draw your M by EI diagram, how it will look like? It will be M upon EI diagram. This is your M upon EI diagram. And now your free end will become fits, and your fits end will be free. Okay. So now this is your beam. For this beam, you have to calculate the support reactions as well as bending moment at any particular point that you are required. So suppose this is our A joint and this is our B joint. So at here, AX will be 0. Okay. And here you will have some BY. So your BY will be equal to BY plus 1 by 2 into what will be this value? This value is PL upon EI. 1 by 2 into PL upon EI into L. That will give you BY equal to minus 1 by 2 PL square upon EI. Okay. So this is the value of shear or first the reaction for the M by EI diagram. Now if you want to calculate the value of moment also, so how the moment will be? So this will be your moment MB. So your MB will be equal to 1 by 2 into PL upon EI into L. This is your load and it is acting at 2L by 3. Okay. So your MB will become PL cube upon 3EI. Okay. So This will become, so therefore your By will correspond to shear at B, and this shear will give you slope at point B equal to PL square upon 2EI. Okay. Similarly, your MB corresponds to moment force of conjugate beam at B, and it will give you the deflection at point B. So your delta B will be equal to PL cube upon 3EI. Please remember, this deflection and this slope are for the main beam, and the bending moment and the shear force that you have calculated is for the conjugate beam. So don't confuse that, since here it is fit support, how the deflection can come at point B. So this deflection is for your main beam. Okay. So this is for your main beam. This is also for your main beam. And this is for your conjugate beam. Likewise, we have to do and determine the value of reaction force as well as the moment at any point in the conjugate beam, and it will provide you the slope and the deflection at the main beam. Okay, so same concept we have also used in frames. So what we have seen in the frames. Okay, now configuration is correct. Let me come back. So in beams, how we differ that of frames, how we can differentiate between the frames and the trusses. So what happens that in truss, load cannot be at the middle of the member. So that is the first differentiating point, that load at the middle element is present. Let me write it as middle location of the element. I think that will be correct. Okay. So load at the middle location of element is present. Second thing is that you can apply not only the point loads, you can apply UDL also. So in frames, UDL loads can also be present. In third, that here joints are not rigid, whereas in truss they are all either rigid or pin jointed. No, mostly they are pin jointed. So how you define a frame is that frame is a structural member which is capable of resisting externally applied load by developing axial force, bending moment, and shear force. Okay. Suppose you have a frame which is fixed at bottom and load is applied at joint C. So it has this length as L, this length as A. So break them into two parts. So you will be having this BC element. So it has force P here. It will provide you the reaction VB. This will be your VB. And the axial force here is FB. And this will be the moment MB. Now this force FB will act as a shear for the beam AB. Okay, so this acts as shear for AB and VB will act as axial force for AB. Okay, so see the free body diagram here. So now VB will be acting along the axis of the member. FB will provide you the horizontal shear and the moment will also be inside the member MB. So from the reaction also you will be having AY, you will be having AX and your moment MA. Okay, so from first thing you can see that your here your VB will be equal to P. This means this will be equal to P and your AY will be equal to P. And if you take moment about B equal to 0, you will be having minus MB plus MA equal to 0. So your MB is coming out to be minus of PA. So your MA is will be equal to MB. This implies your MA will also be equal to minus of PA. Okay. This is how you will solve the problem of frames to determine the bending moment and shear force at different members along its length. That is, if you are taking along the length, it will be the axial force. If you are taking the transverse load, it will provide you the shear force and moment, different moments that are generated due to the external load applied over the frame structure. Now let's solve few problems that will clear your concept for the conjugate beam method that you have covered in this whole week. So first question is telling you to determine this is your the bending moment profile, and you have to draw the loading diagram. So you have to do reverse thing. So it will clear your concepts, because in later stage you have to be able to determine that if you have any bending moment, so what kind of loading is there in the structure. So let's draw the bending moment, the loading diagram, how it will be for this structure. So I will make few lines first. Okay. So now, since here A is having some moment at this point, but suppose if there is any support, you will not be having any moment at that particular point. So it means either there is some fixed support which will be having a moment, or there is some externally applied moment at that particular point. So say we will take the external applied load at that particular point. Okay, so how it will look like. So this will be your external applied moment as ma. Okay, at that point A. So now see, so this is your 2D profile, 2 degree curve, and in the first week we have seen that the UDL will be having the 2D curve along its whole length for the bending moment diagram, because its equation is coming out to be WH square upon 2. Okay, this is for the UDL case. So it means you will be having UDL from point A to point B. Okay, so here UDL will be there from point A to point B. Now from B to C, it is linear, and C to D is also linear. So it means there is something that is concentrated at that particular point. So a concentrated load is there at point C. So draw a concentrated load at point C. Okay. Now from D to C, it is looking like a 3 degree curve. Okay. So it means you will be having uniformly varying load at that particular location. So if anyone has any doubt, please see the bending moment equations for UDL, UVL, point load at different locations. So take any simply supported beam subjected to a UDL at along the whole length of the beam, cut the HZ section, write its bending moment equation, see whether it is a quadratic equation or not. So if it is a quadratic equation, so it means your A to B profile corresponds to UDL. If it is a 3 degree profile, it means your profile of the loading corresponds to uniformly varying load. And if it is linear, it will correspond to concentrated load at any particular point. So this is the loading diagram, so corresponding to the bending moment diagram that is provided to us. So this is how you have to draw. So because suppose what you are doing in conjugate beam method, you are first taking a loading diagram and then finding out the bending moment diagram, and you are taking the bending moment diagram. Sono, can you mute your voice? Some disturbance is coming in between.
Yes, sir. Hello, sir.
Yes, Sono.
Sir, one doubt is there that between D and E, it will be uniformly varying load.
Right.
But I think from D to E, it's I think it will be like I think so. It will
Hmm.
be always varying, sir. But it is look like symmetrical about the center between D and DE.
Hmm.
So
Yeah,
my
you
doubt is
can.
that.
Yeah, if you draw that profile also, that will be valid, but it depends upon the torsion to torsion. So if you draw the uniformly load directly also, like this, that will
Yes,
also,
sir.
be one of the other option, but it will depend
Okay.
upon the kind of means if you have that NPTEL means assignments, you will see that you have
Okay, sir.
many options available. So based upon the options available, you have to select what kind of loading diagram is provided to you.
Okay, so good. Thank you, sir.
So now let's move to the next question. So if you have a statically indeterminate beam, you have to draw the conjugate beam for this given beam that is provided to you. So what we have seen in the previous week that if you have given this is your real beam, so you have to draw its conjugate beam. So for the conjugate beam, your fixed support will become the free support. So first make few lines. Okay. So now your fixed support will be your free support, and so I will write by here. It will be your free support in conjugate beam. It This is a externally applied hinge. It will become internal hinge. Your internal hinge will become external hinge, and this hinge will remains the same hinge. Okay. So how your profile will look like? So this will be your internal hinge. Here you will have one external hinge, and here also you will be having one external hinge. So this is how your conjugate beam profile will look like. Now, moving to next question, you have to determine the slope at point A and deflection at point C. Okay. So for this, I will make a beam. Let it will be having a moment of M at the center, and we have the reactions here. So if we take the moment about this point will be equal to 0. So here reaction will come out to be M by L, and this reaction will be M by L. Now draw the bending moment diagram for this. Okay, so it will look like this part will be in holding condition. Yeah, and then due to that concentrated moment, it will go up, and then it will go down to 0, and it will have a maximum value of ml by 2. This will be negative, this will be positive. This is your A, B, C. This is your bending moment diagram. Now I will take this and draw the conjugate beam profile. Okay. So now draw the conjugate beam profile for this. So how it will look like? It will be same with uniformly varying loads along its length. So now this is the question available with you. You have to determine the slopes as well as the moment at various points that are required for your means that are required to be calculated in the torsion. So here this is your EI M by EI diagram, and here the maximum value of load is M upon 2 EI. I think it is M by 2. I have written ML by 2. It is M by 2, not L. M by 2, and this is also M by 2. Okay. If you calculate the reaction forces AY, this is your CY. Okay. So what will become? Take moment about the. So I think I will write it as B because it is in torsion it is given it to be B. I will write this as C and write it B. Write it B. This will be C. So it will be By, and here it will be Bx, that will be equal to 0. Now calculate any value. So take moment about point B equal to 0. You will be having Ay into L plus 1 by 2. Now this loading will come to EI. What will be distance? Distance will be L by 2 plus L by 6. Okay. Now another loading will also come, that is negative. It is there in anti-clockwise direction. It will be M upon 2 EI into L by 2 into 2L by 6. That will be equal to 0. Solve this. You will get AY plus 2ML upon 24 EI minus ML divided by 24 EI equal to 0. So you will get AY equal to ML upon 24 EI. So this is the value of reaction at A. Now calculate the value of reaction at B. What it will be? So BY will be equal to ML upon 24 EI. Okay. Now, if you have to calculate the bending moment diagram, so take moment about point C equal to 0. Okay. So this will be the profile. Here, this shear will be acting and this will be the moment. And it will have the reaction here as ML upon 24 EI in negative direction. So your equation for bending moment will become ML upon 24 EI into L by 2 plus 1 by 2 into ML M upon 2 EI into L by 2. This is your area multiplied by L by 6. That will be the distance minus M equal to 0. So solve this, you will get M equal to 0. So now what you can conclude? So from this, you can conclude that uh, your theta, we have to calculate slope at point A. So your slope at point A, theta A, will be equal to the deflection at point shear at point A for the conjugate beam, and it is equal to ml upon 24 EI. Substitute the values. You have m is equal to 50. L is given to you as 8 divided by EI value. 24 into E is 200 GPa, and I is given to you as 8 into 10 power 6. So convert them based upon the units available. So you will get theta A equal to 0.01 radians. And since moment at point C is 0, so it will give you delta C equal to 0. So this is how you solve the problem for any deflection or slope at any particular point using moment area method. Sorry, conjugate beam method. Okay. Now let's move to another question. You are having a question wherein you are having a concentrated load of 25 kilonewton provided at a distance of 3 meter from support D. So draw the bending moment for this. So for this, take 25 into 3 from this distance is equal to dy into 6. Okay. First, we are considering only BD portion. From this, you will get dy is equal to 12.5 kilonewton. So if your dy is 12.5 kilonewton, your dy will also come to be 12.5 kilonewton. Okay. So it is like you have a BD beam having a load of 25 kilonewton applied. It will give you two reactions of 12.5 each. Now to calculate AI value, how you will do? So your AI will be 25, you have the loading. D you have coming out to be 12.5 kilonewton. So your AY will also be 12.5 kilonewton. Okay. So now let's draw this. Also your moment at A you have to calculate, because here you have dy, here you have AY. AX will be gone, AX will be equal to 0, and you will be having MA. Now you also calculate MA. So MA will be equal to minus 12.5 into 3, and it will come out to be minus 37.5 kilonewton meter. Okay. Now you have calculated all the forces. Draw the diagram for this. It is like, yeah, you have two reactions of 12.5 kilonewton, and your loading is there for 25 kilonewton. Moment is applied having a value of 37.5, kilonewton meter. Okay. So mark the points. This is your point A, point B, point C, point D. Draw the bending moment profile, or directly draw. We will draw the M by EI profile. So it will be, so here it will be linear up to point B. Yeah. And then it will move like this. So mark the points as A dash, B dash, C dash, and D dash. And this will be your loading diagram. Okay. So this is your M by EI diagram of conjugate beam. Okay. It has a value of 37.5 EI here and 37.5 EI here. Now calculate the value of reactions at these points. So use moment about point B equal to 0. You will be getting 56.25 upon EI into 2 plus 112.5 upon EI into 3, and that will be equal to dy. And what is the distance? Distance is 6 meter for beam VD. Okay. From this, you will get, solve this, you will get dy equal to 75 upon EI. Okay. Now take summation of vertical forces equal to 0. You will be having dy dash plus dy dash equal to 56 upon 25 upon EI. This will give you by dash equal to minus 18.75 upon EI. Okay, so now by dy you have calculated. Calculate moment also. So consider section CD, C dash D dash, because you have to calculate the deflection at point C. So take moment at point C. So what you will get? You will get M plus 56.25 upon EI into 1 minus 75 upon EI into 3 equal to 0. From this, you will get moment equal to 168.75 upon EI. So this moment at point C will give you deflection at point C. Okay. So this is how you can easily calculate the deflection at any point. You have to draw the conjugate beam, and from the moment of the conjugate beam, you will be able to get the deflection of the real beam. Okay. Now let's move to another question. Suppose if you have a different kind of thing, means you have a variance section available to you, then how you will solve this problem? You will be having, you have to determine the deflection at the midpoint. So how you will solve this problem? So now we will use another method, that is unit area method. Okay. So in this, what you will see here, we will have reactions. So now we will draw this beam separately. We mark them as P. Okay. So what will be the reactions? Reaction will also be P. Okay. So this is 2I. This is I. This is I. And now take a distance of x1 from this side, x2 from this point, h3 from this point and h4 from this point. Okay. So now what it will be? You will be having, I think I will write in next page, from 0 to h1 equal to L, you will be having mi equal to p into hi. So if you are taking the whole load as a unit load, so what will be the deflection? What will the reaction at endpoints? It will be 0.5, 0.5. So this is what we are using the Cauchy-Lano theorem. If you have a unit load, the deflection will be written as mm upon ei into dx. Okay. So now same concept we are using here. So it will be 0.5 upon ei. Now when 0 is less than h2 is less than L, so your m2 will become P into L plus h2. Okay, so it will be 0.5 into L plus h2. For the third section, it will be symmetrical because the loading is symmetrical from both sides. So your M3 will become 0.5 into L plus H3. Your M4 will become P of H4 and it will be equal to 0.5 into H4. Now take integration of this in such a way that this equation will be satisfied. Okay. So your delta will become the integration of 0 to L from endpoint. It is phi when there is capital moment without unit load. So with unit load, it becomes 0.5 into hi upon ei into dx. Okay. Plus second area, what you are having is 0 to L by 2. Now in this area, it will be P into L, the whole moment, and the conjugate, the moment in unit beam is zero point 0.5 into L plus h by 2 divided by ei. Since both whole the beam is symmetrical, so we can take it as into 2. Okay. So your delta at mid will be equal to P upon 2 ei into h1 cube upon 3 0 to L plus P upon 4 ei into LH2 plus H2 square upon 2. This will be 0 to L by 2 and whole will be different. Whole will be twice. So here delta B, delta at mid will become PL cube upon 6 EI plus PL cube upon 8 EI plus PL cube upon 32 EI into 2. So your delta mid will be equal to 31 PL cube upon 48 PI. Now substitute the values. You have 31 into what is P? P is 20. L is 2. 20 into 8 upon 48 into E. What is the value of E? 208. 200 10 power 9, 8 into 10 power 6. I think 6 is given, no? 6 to 10 power 12 into 10 power 3. It will become 64.6 mm. So this is how you will calculate the deflection at a midpoint using unit load. So what you have to do, you have to use Castigliano's theorem, in which if you apply a unit load at a particular point where you have to calculate the deflection, your deflection at the at that point will be integration of mm upon ei, where capital M corresponds to the external loading without unit load, and the small m will correspond to unit load moments at various sections of the beam. Okay, so this is how you calculate the deflection using Castigliano's theorem. Now, last question is same that you have already done. It's like you are provided with the bending moment diagram, and you have to determine the loading conditions at various points of the beam. Okay, so now here since the bending moment at end is 0, so it means there will be some support. So we will make a support here. In AB region it is linear, so it means here we will be having a loading. So I will add some load here. So this is my loading. Okay, since bending moment is becoming 0 at point B, so it means there is some internal hinge at that point B. Okay, and from C to D it's becoming quadratic, so it means there is some UDL at point C to D. And reaction also. Yeah, so this completes that. If you are provided with a linear, so this is your linear profile, this is your 2-degree profile, and this is your loading diagram. Okay, so in this week what we have covered, in this week we have covered using the conjugate beam method, how you can determine the slopes and deflection at various points of the beam. In next week we will also continue this uh, conjugate beam method, and we'll try to solve the problems on frames based upon this moment area method, moment area, as well as the conjugate beam method. Okay, so if someone has any doubt, he can post in the student forum, or also can ask right now. We will try to answer in the student forum as soon as possible, and uh, will provide you the detailed description for the same. Okay, so in this week we have covered the topic of conjugate beam method. Next week, what we will try to see, we will try to see the deflection of beams and frames using virtual word method, conjugate beam method, and the moment area method. Okay. So thank you all of you. Hope you have liked the session. Enjoy your weekend.